Hi everyone, I'm Houjun Tang. I'm a computer scientist, and today I will be talking about more of the data management aspect of the EQSIM project. As if you remember earlier, Dr. McKellen talked about data management in his talk, and he was repeatedly mentioning that not enough people are paying enough attention to the scale of the data that we are now capable of producing. So I will provide some more details and how we are managing our current data, how we plan to manage the future expansion of the simulation data sets. So first of all, a brief overview of the data management in our EQSIM workflow. So there are three main components. Component one is where we are producing our data. We run large simulations on big supercomputers. For example, we periodically run our simulations on the Frontier, the exascale supercomputer at Oak Ridge, and then we typically transfer the data produced to NERSC, to the Perlmutter supercomputer, where we do analysis and visualization and things like that over ESNet, which is a fast, provides fast connection from Oak Ridge to Berkeley. And component two is where we do analysis. For example, the structural engineers like Dave, they are interested in performing building analysis using the ground motions we produce in our simulation. And then the third component is for visualization and interactive interrogation of the data sets. So I will hopefully do a demo later in my talk to show we have built a tool to allow us to inspect the motions on an interactive map. So next, so while we are dealing with the simulation, so this is the first part about, I will talk about how we are dealing with simulation. So we chose to use HDF5 as the data format and also the I/O library. And personally, I'm an experienced HDF5 user. I like it, so also my opinion could be biased. And so HDF5 full name is a hierarchical data format version 5. It's a model, it's a library, and a file format. It is has been there existing for over 25 years, and well, why we use it is mostly because of a few reasons. One of this is as we are running simulations on supercomputers, we really need fast parallel I/O, and HDF5 supports that. And also, when our data is after the data is produced, we would like to share with both within our team and with other people, and so HDF5 provides easy cross-platform sharing, so you can access the data in different platforms, Linux, Windows, etc. And also HDF5 has a nice property that it keeps both metadata and data in the same file. So I have a diagram showing a typical HDF5. You can think of it as a container, and with the hierarchical in the name. So HDF5 manages the data and metadata in a hierarchy, just like a file system. So you can have HDF5 groups and nested groups, just like you have directories and subdirectories in your Windows or your Mac machine. And then you can store a multi-dimensional data sets within groups, and you can attach metadata such as the latitude, longitude of the station that this data set is corresponding to. So those are a few of the reasons why we chose to use HDF5 format in our simulation and in our project workflow. So now I will be talking about the main challenges we have. First of all, one of the really big challenges is the data size. So as we are moving, as we are using the utilizing the powerful exascale machines, we can run really large simulations with really small grid size. So a large number of grid points in each simulation, and we can output a large number of data, a large amount of data. So for example, I have at least two examples here. So for the 5 Hz that we have been talking about in this workshop, that's where we are sharing the data. So these are the simulations that produces the data. So the 5 Hz Haverford simulations with a VS mean of 250 meters per second, and we have the 120 by 80 kilometer domain. For running this simulation, if we run it on 512 nodes, then it takes about 6 machine hours for a total of 90 seconds duration of the simulation. And if we output a 2 kilometer spacing, we will have about 2,300 stations our size, and If we store it in HDF55 and if we just store the velocity because that's the default option where the SW4 outputs, it will be about 2 gigabytes each for each simulation, and for the 50 runs will be 110 gigabytes. This is not too bad, so we can still manage it. You can even download things in your computer or even just your cell phone. And for the peer database, the SGMD database, it stores in the ASCII format, and it stores velocity and also acceleration and displacement in the for normal, for parallel, and vertical direction is a little over 700 gigabytes, still somewhat manageable. And however, if we switch to a final resolution where the grid size of our simulation, so the top surface grid size of our simulation is 6.25 meters, and that results in 246 million grid points just for one simulation. And to reduce the size, just by downsampling on the time dimension, if we downsample it by a factor of 16, and then we reach to a delta between time steps of about 19 milliseconds, it's about 25 terabytes each. So that's already enormous. And if we account for all 50 runs, then it's 1.2 petabytes, which is really prohibitive. There's no way we can ask for that much storage on a supercomputer. Maybe they can, but it will occupy a significant part of the entire data system. And also, it will be almost impossible for us to maintain long term, and also its data is just too big. And then if we are looking for into a little bit more into the future, if we perform 10 hertz simulation, same with mean 250, then because of the increased hertz, we will need to refine the grid size. So the top surface grid size will be a little over 3 meters, and now we will have 1 billion surface grid points for the velocity motions. And even if we still do some downsampling by 15x, when we reach to a delta t of 9 milliseconds, it will be 208 terabytes each. So, and that's just for one simulation. Ideally, we really want to have at least 10 of them, so that's even more data to be stored. So here's a kind of a line trend of the data sizes. So if we want to do something further, 10 realizations of 10 hertz, and if we want to reduce the VS mean to 140 meters per second, then just 10 of those runs will produce 3.2 petabytes of data, which it's just too big to handle. So what are we going to do with that? First of all, we want to do really significant amount of data reduction. And currently, the state-of-the-art data reduction, or the more popular data reduction techniques, is compression. And in compression, there are two main types. One is lossless, one is lossy. So as the name suggests, lossless compression preserves all the information. You compress the data sizes get reduced, and after you uncompress, you get the exact copy of your original data. So that's lossless compression. And then there's also lossy compression. Lossy compression usually comes with an error bound. So you can set an error bound, and the compression algorithm will respect that error bound to compress the data. And but the thing is, you will lose some information during that process. So the data you decompress will be a little different than your original data. So here I have an example. So both lossless and lossy compression, typically they split data into chunks, and they utilize the spatial and temporal locality of the similar values in the chunks. For example, in our simulation data, the data velocity values of neighboring grid points, they tend to be very similar in value. And the compression algorithm, they can take advantage of that and use less number of bytes to represent the data. So for example, a popular approach, kind of oversimplified approach, is you have a series of values, or here there are 4 values, and since they are very similar, you can just calculate the deltas of the values so it subtracts the first value of the 3 other values, and you get a delta, and you represent that delta with fewer number of bytes. So overall, you are getting a much smaller size. For example, originally, if we stored it as 64-bit floating points, we need 32 bytes, and if we compress it, it may end up as 20 bytes. You get a data reduction. So as I mentioned, the lossless compression will preserve all the information. For example, the 1.401, you compress it and you decompress it, you get the exact same 1.401 value back. But the lossy compression, you will discard some information. So the same value you may, when you compress it and you give it an error bound of 0.01, depending on the algorithm and depending on its neighboring values, after you compress and decompress, you may get values like 1.407 or 1.399. They are all within the 0.01 error bound you specified, but it's some difference when comparing with the original data. So the thing with the lossless and lossy compression is, with lossless compression, since we are preserving all the information, we have to use more bytes for storage to preserve those information. So typically, the lossless compression, the most you can get is a factor of 2, maybe 3 or 4 in rare cases. And for lossy compression, because you lost some data, so you can compress things much smaller. So lossy compression, you can get as high as 10 or even 100. And so in our case, lossless compression, the factor of 2 is not an option, because if you remember, we talked about petabytes of data. Even if you cut it by half, it's still too big for us. So that's why we are looking into applying the lossy compression. And here, for the 50 simulations that we have been talking about, we use the lossy compression error bound of 0.01. And if you can see on the bottom of the page, the two figures shows some comparison of the compressed data and the original data. So mostly it looks pretty good in these cases. So currently, so we just settled for the error bound of 0.01. That's 1 centimeter per second for the velocity values that we are producing. So using this lossy compression, we have significantly reduces the total size of our simulation output, the entire surface grid points. So for example, for the 5 Hz runs, for the 50 runs previously was, the uncompressed data is 1.2 petabyte, and we were able to compress it to just 14 terabytes. So this is actually both with lossy compression and the time downsampling with a factor of 16. And similarly, for 10 Hz runs, the one run that produces 200 terabytes data, we can effectively compress those to just 4 terabytes. It's much more manageable, and we have the storage space to store them for long term. And same figure as the trend in the previously. So for the 10 realizations of 10 Hz runs and VS mean of 140 meters per second, uncompressed data, it will be 3 petabytes, and if we compress it and we have somewhat reasonable compression ratio, we can reduce it to about 74 terabytes, which is somewhat manageable. And the next thing is we have compression, but we also want to optimize the data output speed during simulation, because typically when we are running the simulation, we run this on hundreds and thousands of compute nodes, and any time spent on I/O will be multiplied by that factor. So we get charged for using the supercomputers. We get charged by the node hours, and our project is only allocated for a certain number of node hours. So we want to utilize that efficiently, and that's why we need to optimize the data write. So we use a few strategies to speed up the data write. First of all, we use the HDF of data chunking. So data chunking it is also required for compression, because if you remember, I previously mentioned compression works on data chunks. So you need to split the conceptually 3D grid into smaller chunks and write data in those chunks. And by writing those, and also the chunks corresponds to the data decomposition when we are running the simulation with hundreds and thousands of nodes. So the data chunking results in more contiguous writes, which is good for the current file systems. And we also do data buffering. So we don't want to output data for every step, because then it's also resulting in very small I/O. And the existing HPC file systems, they don't like small I/O. Small I/O takes more time. So we do buffer the data. For example, we buffer every 400 or 800 steps, and that aggregates to more data per write, and is more efficient. And we also do asynchronous I/O. So asynchronous I/O means we are overlapping the I/O time with the computation time, and this is especially useful when the majority of our computation happens on the GPU, and the CPU cores are often idle. So we can utilize those idle CPUs to write the data as the simulation is performing on the GPUs. And also, I mentioned earlier that we often perform our large simulation runs on Oak Ridge on Frontier, but we do the long-term data storage and also data analysis on NERSC on Perlmutter supercomputer. So we do need to transfer data between the HPC facilities, and we are utilizing the ESNet, which is a high-speed network connecting among the different HPC facilities. And one way we found that is useful is to take full advantage of the fast ESNet network. We need to split the big files into smaller chunks to transfer them in parallel and to be more efficient. So we found that splitting the one big file into 2 GB chunks and transferring them in parallel is the fastest, and we can transfer the 290 GB data in just less than 1 minute from Oak Ridge to Berkeley. And the next thing is, so once we have the data transfer, we want to do some analysis, and we want to do some visualizations. So because of as I mentioned earlier, we are optimizing, during the simulation time, we are optimizing the data write performance, but that may often create a different access pattern with the visualization or analysis needs. So there is a mismatch, and the mismatch will cause a much lower I/O performance. So here, a brief example is when we are writing the data, the write optimized, we are doing the chunking with the time XYZ layout. But during visualization or when we are doing individual analysis, it often requires just XY cross sections, and that will make the access, the mismatch will cause a slower I/O. And also another thing is, if we perform the data access in serial, it will be too slow for the data sets that we have. So for example, one thing we do a lot is we generate an animation of the simulation runs, and if we do a serial processing, the generation of the animation will take hours. And if we do it parallel, and if we optimize it and do the access based on chunks, it's much faster. So here is an example. So I will just play on the right-hand side is the animation from one of our simulation. So to generate this simulation, we use 2 horizontal components, and we do the square of the sum of the squares of the 2 horizontal components. And there are in total 190 GB compressed data for the 2 components. And if we uncompress it into memory, because we have to do that to operate on them, that's 9 terabytes. So to make this animation, we further downsample in time. So because for animation, we don't need too high of the frame per second. So this animation, we use about 25 frames per second. So that corresponds to a factor of 2 in time. And we also spatially downsample for a factor of 10x. So, and that produces good enough resolution for us to inspect. The original serial code processing will take more than 10 hours. And if we parallelize it and run it on Perlmutter, we can perform this animation generation in just 7 minutes with just 8 Perlmutter nodes. And next, so this is something we developed internally for our internal use. So let me see if I can do a live demo. So this is a tool I mentioned earlier that we have developed for an interactive inspection of ground motion. So as you can see, we made a web page that is just an interactive map, and we have different components. First of all, we can play the animation that we just saw. This is basically overlapping on the corresponding region. And besides that, we also output some interesting things to look at. So for example, for this simulation, we have a predefined special marker that filters only the sites with larger than 1g acceleration. And if you click this marker, it will pop up a window, and you can inspect the acceleration values. Then there's also the 2-kilometer spacing where you can see all of the sites. And if you zoom in, you can find the location and click on individual markers and just have a quick inspection of those motions. And there's also plotting a PGA that's across the domain, where you can just quickly glance through the hot regions where there are large PGA values that you may want to look into. So this is just a tool we have developed, and hopefully we can open this up to public access, but for now, because it is currently hosted in a small server, so we need to evaluate how much traffic that server can support, and not just opening it up and everyone crash the server and nobody can use that. So going back to my presentation, that's basically all I have today. So in summary, we use HDF5 for the EcoSim project in the workflow for its efficiency in HPC, and also for compression, and for supporting or keeping the large data size, we need lousy compression, and we have some early experiments with setting the error bound. And for processing the large amount of data, we need to be careful how to access them in the most efficient way. And we have some tools like the EcoSim Wiz for a quick inspection and interactive browsing of the data. So that's it.
Thank you, Houjun.